Welcome back, everyone. It's been a fairly long day, I think, for everyone who's stayed through all the presentations. So our next session's on landfill management and design. We have 2 presentations left to end the day. And Tyler Anderson from Bishop Water Technologies is going to moderate this session. And I'll be back at the end to close the day. So Tyler, you can take control.
All right, sounds good. Thanks, Joe. Yeah, thanks everyone for joining us again here. My name is Tyler Anderson. I'm a project manager with Bishop Water Technologies. We're based in Renfrew, Ontario. I do work in the environmental remediation field all across Canada. We're fortunate to just do a presentation in the water section a few minutes ago as well. Maybe some of you caught that. Anyway, looking forward to this one on landfills here that we have coming up. So I'm going to pass it over to Trevor here, and he can take over. So here you go, Trevor.
Okay. I'll show my screen. Okay, so I'm Trevor Mahoney. I'm currently working at XCG Consulting Limited. I'm actually broadcasting from Waterloo, Ontario, so just outside of Toronto. So I'm going to turn my camera off here while I do the presentation, but I'll flip it back on for questions if anybody has any. I'll kind of try to answer them in person. So I wanted to go through the landfill design, cell design. So I'm going to start out with a brief overview of the basics of landfill design. So we're going to go through some of the items that constrain your landfill size, and then a brief overview of some of the design components and kind of how we arrive at deciding on those components. Then I'll go through some project or a project example using Alberta Pacific Forest Industries. We recently completed a design for their landfill expansion, and it's currently under construction right now. So it's kind of a good relevant project to use. So the basics of landfill design. So a lot of a landfill design is made up of the area that you can put your landfill. In this case, the area that I'm kind of highlighting with the laser pointer is the entire landfill, not just the cell. What I wanted to show here was setbacks and the landfill footprint. So the outline of the landfill. With this example, we were constrained by a handful of gas and oil pipeline easements. So the actual facility over here that required the landfill is up over here, and we decided to put the landfill over in this corner. Another item or two that limit your cell design is hydrogeological and geological restraints. So hydrogeological, a lot of your permits and stuff will let you know you can only go so close to the groundwater table, whether it be seasonally high or the information that you have based on historical testing. And the geological restraints typically involve there being some degree of clay, sometimes with a specified permeability below your base grade. Sometimes it's a little bit looser on what they'd like to see as the permeability. But depending on your permeability, you're going to have to make some changes in your overall design. So one of the other ones is the existing site infrastructure. So this one here, basically you don't want to put your cell too far away from where people are going to be entering the site or where you're actually going to want to truck the waste from. So again, back to our example here, the facility that wanted the landfill is a short truck route away. Try to keep it as close to your facility as you can get, but obviously if your permit doesn't allow it to be that close, then you kind of have to put it where you can. And the other thing, more importantly, is your regulatory and your approval requirements. So with this example here, I kind of highlighted the option 1 and the option 2. This is actually from a draft permit for a landfill that we worked on. So option number 1 was a minimum of 1 meter engineered clay with a hydraulic conductivity of 10 to the -9 meters per second with a HDPE geomembrane above it. The second option that we could have gone with was a geosynthetic clay liner, which is basically a fabric with bentonite, an artificial clay woven into it, and then that same high density polyethylene liner above it. So if you're thinking of the difference between the two, your geosynthetic clay is millimeters thick, whereas your 1 meter of clay is obviously 1 meter. So you're losing a significant amount of capacity for your landfill by going with option 1. So a lot of places they'll end up going with option 2 just to get that 1 meter across your entire cell back as far as airspace. So these are items that we typically take into consideration when we're looking at the design of a landfill cell. So obviously your approval, which basically guides you step by step the items that you need to consider when you're putting together your landfill design, be it a specific expansion or if it's a design of an entire landfill. So your topography, geology, hydrogeology, and climate review. I've got a screen grab here of the HELP model, which is a rather archaic program for estimating the hydraulic performance of your landfill and all of its components, but it's still the most relevant tool for estimating your leachate generation rates, how much precipitation is going to make it through your liner, and your cap once it's closed. And site investigations and soil analysis. So basically what we've got here is a borehole log showing some clay till and a stiff sand and gravel up at the top. Some other considerations, your base contours are the grades for the landfill cell. So like I said earlier, you've got to figure out how close to the groundwater table you can get. And then basically you're going to create a low point for your leachate to flow to, and that low point is your controlling factor. It's typically the sump or the low point that can't get any closer than a couple of meters to the seasonally high water table. Your liner design for the environmental containment. What we've got here is a typical landfill liner. So here we've got 600 millimeters of compacted clay liner, HDP geomembrane, non-woven geotextile, and then a drainage stone with another geotextile above it. And you've got to take into consideration your leachate generation assessment and leachate collection system design. So again, here on the screen, we've got the standard liner components, but we've got a perforated leachate collection pipe running through the center of your cell to convey the water to the sump. You've got to take into account your surface water management. So all the rainwater that falls on your closed landfill as you progressively close it, you're going to have to deal with it via ditches. The ditches will typically carry it to a surface water pond where sediment and any impacts will drop out, and then it gets tested prior to releasing it to the natural environment. Another main concern is staging, access, and materials management. So here I've got a project that was done a little bit closer to home here in Ontario, where they had to lay out a whole bunch of pipe works. And so basically we had to take into account how our expansion was going to look, giving the contractor enough room to lay down the materials that they're going to need. And obviously the stack of $100 bills is the construction cost estimate. Like everything else, you've got a budget and you've got to kind of stick within that budget. So if you build it too big, your construction costs go over your budget. If you build it too small, it saves you a little bit of money, but you're going to be expanding a little bit quicker than maybe you would have if you built it a little bit larger. So those are typically some of the design constraints that we look at when it comes to how to locate a cell, what your typical design elements are with landfill cells. So I'll move into our project example here. So the example is, again, the Alberta Pacific Forest Industries landfill. It's located in Boyle, Alberta. So we undertook the detailed design of what is the 2020 landfill expansion in 2019. All the files were submitted and tendered earlier this year. And as I mentioned earlier in the presentation, they're actually in the construction phase right now. So the project included a conceptual landfill design brief and then staged detailed design of a new engineered landfill expansion. The stage detailed design included drawings, specifications, and a quality control and assurance plan for the construction of the landfill. So prior to deciding on the actual expansion, along with Alberta Pacific, we undertook some evaluation of different options that we could look at to possibly postpone the construction of the new landfill cell. One of the items that we looked at as part of that evaluation was extending an existing berm vertically and a little bit horizontally in order to gain us a little bit more airspace. So what you're looking at on the screen right now is the magenta line would be the top of the new berm, and the gray area at the bottom would be where we would have moved the perimeter road out. So to look at it in a cross-section view, to kind of look at where your gained airspace or capacity is the next slide. So on here, the red items are before we looked at what we proposed. So this is the existing berm, the existing perimeter haul road, and this is your 5-to-1 final contours running up the side slope of the landfill. If we simply raise the berm 2 meters and we maintain the same side slopes of the berm, the perimeter road obviously moves out, the berm gets higher, wider, but you get this sliver of waste here that is increased capacity. So a 2-meter height on the berm would typically result in about 1.8 meters thick layer of waste. And although you might not be thinking that that's a whole lot of actual space, you've got to project that out over the entire, I'll go back up one slide, but the entire side slope here of cell 2B. In the case of the Alberta Pacific landfill, it really only would have gained them about 1 year's worth of airspace. So it didn't really make a whole lot of sense for Alberta Pacific to buy themselves 1 year. This kind of an evaluation or this option would be used maybe for a municipality that's in the pre-planning process as far as an expansion, and just kind of wanted to put that expansion off for 1 year just to get all their approvals in place. But this option wasn't really considered too much for the Alberta Pacific landfill. So what they went with was the new landfill cell constructions. What you can see here, the gray is the cell 3B expansion, and this just kind of shows you the effect that the expansion has on that sliver of waste. So the red again was the cell 2B berm, the haul roads removed. This is where your final cover would go up for 2B, and now this shaded in area is all the area that you gain by expanding a new cell instead of just bumping that berm up. So this option here actually increased their landfill filling capacity by several years, and so that's why it was the chosen option for the Alberta Pacific landfill. So the other thing that we completed was a slope analysis. The permit for the Alberta Pacific landfill stated that they had to use 5-to-1 side slopes for their final waste. We undertook an analysis to see if 4-to-1 or 3-to-1 side slopes made a significant difference in the waste. And right off the bat, we knew that it would. Obviously, it's intuitive. So again, the red is existing. This blue area is the gained airspace if you go to 4-to-1. The purple and the blue would be gained if you went to 3-to-1. The problem is when we undertook a geotechnical assessment, given the composition of the waste and the surface water and all the infiltration factors, the geotechnical firm came back and said that they would be fine with 4-to-1 slopes, not 3-to-1, but we would have to include surface water benches. So what's shown here is 4-to-1 side slopes, but every 20 to 25 meters up the side of the landfill, we would have had to have cut in a surface water bench. There would have had to have been some piping, a means to convey the surface water down to the bottom slope of the landfill without it infiltrating or running across the side slope, like sheet flowing across the landfill. So part of this analysis was looking at what the gained airspace was by going to 4-to-1 and including the benches versus staying at 5-to-1. And one of the key factors that played into it is it would have had to involve a permit application and modification. And when we looked at 5-to-1 versus 4-to-1 with the benches, the increased capacity shown kind of between the blue and the red lines just didn't make financial sense to go through the process of 1, applying for the permit change, and 2, the increased cost of the pipe works and all the other infrastructure that would have been required to safely convey the surface water from the surface water benches down to the bottom of the landfill or the perimeter ditch at the bottom of the slopes. So again, the decision was made to just stay at 5-to-1 side slopes and kind of forego that extra capacity. The other analysis that we took into account was tying into the older leachate collection system. A lot of landfills that we work on, their systems, their leachate lines, their drainage rock, a lot of the components that we talked about earlier have been in place for several years. And that's the case with the Alberta Pacific landfill. And a lot of those elements tend to deteriorate. They'll lose their structural rigidity, so your HDPE pipes will they'll oval on you. They'll shift. The landfill's constantly moving, and the grades are constantly moving. As you pile waste high up, it exerts a force down, and you'll actually get a little shift in your landfill grades. So it can often be difficult to find the tie-in points between your new and your existing landfill leachate collection infrastructure. So the solution that we went to was to break the landfill into a couple of different parts. So the area at the top with the gray, they're labeled cell 1A, 1B, and 2B. That's the existing landfill. And we decided to just leave it as its standalone as far as the leachate collection system. What we did in the design brief, or the initial part of the design, was to go in and design the future cell 2A, 3A, and 3B. We connected everything with their own cell 2A, 3A, and 3B have their own leachate lines that come together to a common sump down here in the southwest corner of the site. And all the infrastructure for this cell was kept separate from the existing 1A, 2A, and 2B. So the decision was made to almost kind of make two separate landfills as far as the base is concerned. But when the final contours are projected up, it would then look like one continuous landfill once it was filled. So the final issue that you have to look at is your climate challenges. One of the issues being in Boyle, Alberta, is the construction season is fairly short, and when winter hits, it hits harsher than other areas of the country. So you have to put down a frost protection layer over your geosynthetic components. So your non-woven geotextile and your geomembrane, and also the clay to protect it from freeze thaw and it cracking, and then basically provides a preferential path for the leachate to get out. So in Alberta Pacific's case, 2 meters of frost protection was recommended. The landfill or the facility only produces about 52,000 cubic meters of waste a year, and the size of the cell with the 2 meters on top of it for frost protection was just under 100,000 cubic meters. So we needed 2 years worth of waste in order to get decent frost protection. So the solution was to start stockpiling as soon as Alberta Pacific knew that they were going to be in need of the frost protection. And also, the previous slide shows the existing contours being a little bit steeper than their 5-to-1. So the plan is to lay back their slopes back to that 5-to-1 and kind of remove some of their stockpiling in areas in order to get to their 5-to-1 and move that excess material down onto the cell floor. One of the ways that you can go about planning for this is, again, limiting the size of your cell. So this figure here, all that's being constructed this construction season is just cell 3B. So the line will be divided down through here. Instead of taking on this entire area and knowing that A, you would have to cover it with frost protection, and B, you're leaving a lot of open area where rainwater is going to fall. It's going to create leachate, and that's going to drive the cost of your leachate treatment up. It'll just add to the costs, where if you just kept your cell size smaller, a little bit more contained, it'll actually bring your costs back down to a reasonable level and a little bit more manageable as far as the leachate production rate. So that's what I had for the presentation. So I'll flip my camera back on. If anybody has any questions, I'll answer them now.
Yeah, Trevor, thanks for the presentation. That was really well consolidated and put together. Nice info for sure. We actually don't have any questions showing up here in the question box yet, and that might be partly my fault because I passed it over to you right away without doing a little bit of housekeeping at the start. If anyone wanted to ask questions, question box in here, and you're welcome to include them there. I don't know that we can turn on the mics for people, but just type them in there. And also Trevor's contact information is available here through through EnviroTech as well. So if someone had a question that they wanted to follow up directly with Trevor afterwards, oh, here we do have something come up here now. Okay, does the design criteria take into consideration the waste type?
It can, yes. A lot of the makeup of the landfill base is fairly standard in that it's almost common practice now to have a geomembrane, a clay underneath of it, or the synthetic clay, and then a drainage layer of some sort. But it does affect some of the other components. For example, we've had a couple of landfills in the past that they dispose of ash, and you have to evaluate the ash's effect on the clay material and any synthetic materials that you have beneath that. So if they're more acidic, basic, they can degrade your synthetic materials quicker, and you have to take that into account when you're designing it. So a lot of the synthetic material producers have now specific products that are geared towards specific wastes.
Okay, thanks, Trevor. We do have a couple others here now as well. And that question was from Brian. Now we have one from Brittany here. What are some of the characteristics of the leachate that a landfill might experience? Is there a risk of the leachate dissolving the bentonite in the geomembrane? Yeah, good question, Brittany.
Yeah, so again, similar to the last answer, a municipal solid waste, if you're just talking about like standard curbside waste taken to the landfill, you're probably not going to run into a lot of issues with the leachate breaking down your synthetic materials, specifically the bentonite. But again, the Alberta Pacific one is a fly ash material that's produced from the pulp and paper industry. We've had a couple others where we've had to run analysis on the leachate to make sure that the bentonite materials don't break down. We've had to select a couple of different bentonite or geosynthetic clay liners to accommodate the varying chemical constituents of the leachate. But in a general sense, a municipal solid waste, you're not going to run into a whole lot of issues with it breaking down the bentonite. But when you start getting into your specialized fly ashes, pulp mill byproducts and stuff like that, then you'll definitely have to run an analysis on your leachate that it's going to produce and its effect on the synthetic clays.
Okay, thanks for the question. Thanks for the answer. We got two other questions here from Megan. What kind of material is used in the frost protection layer?
So the frost protection layer is just the waste from in this case, the pulp and paper process. So it's the fly ash. It gets mixed with a bunch of other products that are a result of their pulp and paper mill, and then just put out in an even layer. Basically, all you're doing is you're just providing a physical 2 meter barrier. In a municipal solid waste scenario, it would just be what's known as a fluff lift of municipal solid waste. So you're going to want to make sure that there's not any long, hard items that could get pushed down through the drainage rock and puncture your liner. That's why the term fluff lift was provided, because you want it to be fluffy garbage and not something that could puncture your liner. But again, you just put down, depending on the climate in your region, that lift of frost protection. But it's nothing specific. It's just the waste that would go into the landfill otherwise.
Okay, thanks. And one more question from Megan. Did you end up adjoining cells 2B and 3B or keeping them separate because of the older leachate collection system?
So 2B and 3B are separate. If I go back up one slide, I don't know if I can go up one more slide. So 1A and 2A have a connection, a leachate connection channel designed into them. Once we get into detailed design for 1A and 2A, the decision will be made whether that actual connection is going to be put in, but it is planned for. The unfortunate part is I believe that Alberta Pacific has 15 to 20 years worth of site life right now, so it may not be myself that works on that design, depending on when I retire. But yes, the plan is to have them connect together in 1A and 2A, but not 2B and 3B.
Okay, thanks, Trevor. That's all the questions that I'm seeing there for now.
Okay.
Oh, sorry, one more. Another one from Brian here. We got, where are we at for time? Yeah, I guess we have another couple minutes here. Do you encounter issues with the HDPE when they are joined together?
Yeah, so the biggest thing is planning your future expansions properly helps the next cell construction. A lot of times when we're doing an expansion, we recommend like putting if it's going to be just not left open, but like just have a layer of soil put over it. We recommend some plywood be put down over top of the membrane, so when you expose it, it's kept clean from all the dirts and stuff. In our typical design, the liners come up and go down into an anchor trench on a berm, and so that gets backfilled with soil or a kind of a pit run material to anchor that in place. So when you pull that out, you do have some excess soil or some excess material in that anchor trench, but it does deteriorate. It's up at the top of the trench. It has like minimal cover over it, so it does deteriorate. So there is a lot of care given to that tie-in, and a lot of the liner companies do plan for a little bit of extra time going around that tie-in to have to deal with small pinholes, larger holes from rocks, holes created by heavy equipment, machinery, trying to scrape the liner off if the excavator operator gets a little bit too close and snags it. And the machines that weld the liner together typically don't run very well across that tie-in, and so they usually have a lot of repairs to do along there. But any care that you can put into your current landfill liner that would help future expansions, it's always recommended.
Okay, great answers, Trevor. Thanks for taking the time with us for that. And
right.
Thanks for
thank you.
Yeah, that wants to reach out to Trevor afterwards, feel free to do so. And we'll move on to the next presentation. So I'm going to shift over to Franz at Tetra Tech. So Mandy Parker and Franz Hettinga of Tetra Tech are here to deliver their presentation on using a holistic approach. Finish that. Franz, did you get it there? Yeah, okay, that's good. Okay, using a holistic approach to assessment and management of an historic landfill.
Perfect, thank you very much. Franz, if you could go to the next slide, please. Thanks. So I'm Mandy Parker with the City of Lethbridge, and I'm going to introduce you to the City of Lethbridge, talk about historical and current landfill practices, specifically our north side closed landfill. And joining me is Franz Hettinga. He's the principal scientist at Tetra Tech Canada, and he's going to talk about the good stuff, the conceptual site model and the technical components. Next slide. So Lethbridge started out as your typical prairie town. It was built around the Canadian Pacific Railway, coal mining and agriculture. In 2019, we exceeded our population and broke the 100,000 barrier in our April census, which was exciting. Lethbridge has 2 research stations. They're federal, the Canadian Food Inspection Agency and Alberta Agriculture and Agri-Food Canada. We have a university, a college surrounded by agriculture. We have the agri-food industry, which within the city limits includes a few like Cavendish, Richardson Oilseeds, Bayer Crop Science, Black Velvet Distillery, Maple Leaf Pork. And there's others outside of the city limits like McCain's, too many to list. We've got the hospitality and the service industry as well. There is some oil and gas, although it's not really that prominent close to Lethbridge. Our waste management has changed over the years. If you take a look at the photo, this is downtown Lethbridge as it was back in the 1900s. And in the background, you can kind of see coulees, and that'll play kind of into our waste management because we didn't have to dig a lot of holes. We typically dumped over the edge of the coulees. Next slide. So this is our active landfill. It is outside of the city limits. It was previously called the Lethbridge Regional Landfill, but since it's more than just a landfill, the name has changed to the City of Lethbridge Waste and Recycling Center. Some of the features are scale house, Class 2 landfill, industrial soil cells. We have a closed Class 3 landfill. We've got an admin building, a shop, a waste transfer station, which is required for windy days. If it's over 70 kilometers an hour, we have to bale our waste. a Class 2 compost pad, material recovery facility for our curbside recycling program, a public drop-off so people don't have to go to the face of the landfill anymore. Municipal solid waste and household hazardous waste are disposed there. We've got a construction drop-off, which takes shingles, concrete, freon items, wood, drywall, etc. And we have our education center, which is called the Blue Sky Center. Future projects would be our landfill gas capture system, our hydrovac disposal, and organics processing. And this, our landfill where our disposal cells are, it's kind of the last of the coulee fill landfills for the city of Lethbridge. Next. Up until about the late 1990s was when coulee landfilling was the predominant practice. All of the suspected and confirmed landfill sites have been located in coulees. So if you take a look at the picture here, the 2 stars that you see are the 2 closed landfills that we know about. And the purple clouds are the ones that we suspect would be landfills or dump sites. They're not confirmed yet. It's very difficult. There are no records on construction or operations. And the only way we're able to actually locate these landfills or potential landfills would be from newspaper articles from the early 1900s, or maybe municipal complaint records that we found, and this all predates 1950. And those would be in our archives. Next. So here is the north side closed landfill. This image is from the 70s. It may have been a dump site prior to the 70s, but the city owned the site in 1972 and took it over from a private contractor. So our records kind of start around 1972, 73, although limited. The waste at this site, this is a coulee fill site, and you can see the coulees around it, is up to about 35 meters thick. There is an AltaLink substation and transmission lines. You can kind of see that there. The river is about 1 kilometer away from the tow berm. And while we can't confirm, we don't believe that there is engineered liner, but the natural soil's permeability is around 3 times 10 to the minus 9. So it kind of acts a little bit like a liner. The landfill accepted pretty much any kind of waste in the 70s. And there was a liquid lagoon just west of the substation. Next. The site, the north side closed landfill, is pretty much vacant parkland. It's in a coulee. It's the only things that we have near it are our recycle station and the AltaLink substations. There's 2 of them there now. We have a 300-meter setback from the waste boundary. Groundwater, leachate, landfill gas has been monitored on the site on an annual basis since 2001. We did some cap repair and drainage improvements in 2014. There's a landfill gas passive venting trench that was installed in 2014, and we're in the process of updating the risk management plan for the site. Next. We do have some historical reports on the site. We're not really sure what was done pre-2000, but we do have a good handle on everything since 2000. So there's a few historical reports. You can see the solid black line in the image that shows the landfill boundary. The drainage system on the steep slopes that was done in 2014 is visible on the left side of the figure, and that's kind of, that's the west side of the site. The wells are red triangles and black circles. So the gas wells are the triangles and the circles are the monitoring wells. The topography shows that the site's relatively flat on the right side, which is the east side of the landfill, and it becomes steeper into the coulees on the left side, which is the west side. Next. We continue to monitor the site. We've been working on some leachate extraction trials. We've been updating the risk management plan, which includes the completion of a conceptual site model, and Franz will detail that later. Next. So this is not your typical contaminated site. It will not be remediated and it will not go away. To understand the landfill and its contamination, You have to really become one with the landfill. You have to know its age, construction practices, waste types, the municipal culture at the time of filling, the era that it was filled in. You need to understand the receptors, the pathways, the geomorphology, and the best practices at the time. Next, over to you, Franz.
Thank you, Mandy. Yeah, so the Northside closed landfill, what we have been doing over the years is monitoring and slowly building a conceptual site model, which is basically a description of how the site behaves, what the impacts are, what the pathways are, and whatnot. So we did it over the course of years with several drilling programs. Most recently, actually this spring, we installed a couple of more wells to assess the groundwater and groundwater quality and identify the stratigraphy further. We have identified that there is actually clay underneath the waste, and these are a couple of tubes that we took from the waste, and it's from underneath the waste, and it's definitely a nice, fairly plastic clay where we took this sample. But the geology is complex, and this goes for the entire part of Lethbridge, where you have fairly excessive thickness of glacial tills, various sequences. The groundwater table is typically deep. We have sometimes discontinuous groundwater table in the glacial sands and of the glacial silts and sands. And underneath there is a pre-glacial sand and gravel, which is called the Saskatchewan sands and gravel. And underneath is bedrock. One of the pictures of the basal till is here. It's really dark because there's lots of shale particles in. You can see there's pebbles in it, but it's a very tight material. This is hydraulic conductivity 10 to the minus 10. However, there is of course issues with fractures in these till materials. So some of the permeability is not clearly defined. And underneath there is the Old Man Formation bedrock. What you also need to understand is the coulee setting, in which basically, other than a normal landfill, closed landfill, where they used to fill waste in trenches, we have a very deep vertical profile and also a very deep groundwater table. And then the bedrock, which is quite impervious, is actually above the level of the Old Man River. So as far as the sources of impact, of course there is the landfill waste. In this case, it would mainly be municipal solid waste, but in fact, what Mandy said, they accepted everything at that time. Of course, the leachate that is present within the waste, which was already present when they actually filled the landfill, or due to precipitation or ingress of groundwater. There is the landfill gas, including non-methane organic compounds, like volatile organic compounds, for instance. We know there's leachate in significant thickness, way more than we accept for operating landfills, several meters in the central part of the coulee, and it has a variable composition across the site. We also know that that there's various release mechanisms and pathways possible. You can have erosion of the cap, potentially exposing the waste. You can have runoff. You can have leachate infiltration, and groundwater migration to offsite receptors. And of course, there is the issue of landfill gas emissions. So these two figures show a little bit how the conceptual site model is of the basis for the conceptual site model. The original grade is basically the coulee with the various glacial deposits. The waste was placed in that coulee behind a soil berm, which we don't fully understand how it was built and whatnot. There's of course a cap over top, and then there is the sands and gravel, which are mostly unsaturated, so it may or may not form a confining or like a barrier for migration into the bedrock. And then the Old Man River is about 800 meters further to the west. This three-dimensional image, and if I was smarter, I could probably spin this on the screen. Shows a little bit where the waste was placed in this light area. We have the berm here. We have the monitoring wells. We have monitoring wells down gradient, and we have the Altalink service station of substation and the recycling depot. And then residential areas are at about 300 meters to the east of this. A lot of information in this image for the conceptual site model. Basically, release mechanism for leachate, landfill gas, and erosion. Contaminants of potential concern would be nutrients, metals, inorganics, petroleum hydrocarbons, volatile organic compounds. For landfill gases, methane, and the various VOCs and climate change effects. We know that methane is a very strong greenhouse gas. Erosion of materials. It can go to the groundwater. It can seep into the surrounding land or surface of groundwater and surface water. Migration of landfill gases, receptors, aquatic life, water well uses, site uses, and then we have identified various exposure pathways. The details of this are in various reporting, and I won't make any further comments on that in this presentation. The monitoring program consists of landfill gas monitoring using soil vapor probes, which basically are usually nested with a shallow and a deep screen in which we can measure the pressure and the gas composition. We do the leachate monitoring and sampling. We do groundwater monitoring and sampling. And while we do this, we typically look for seepage at the base of the landfill and erosion of the cap and whatnot. In total, there is about 60 soil vapor probes, water monitoring wells, and leachate wells. The challenge for this site is the steep topography and the difficult sometimes to access the places where you would want to install monitoring wells because of the basically the slopes and depth in which you have to drill. If you drill on the top of a coulee, you basically have to drill dozens of meters more than if you were actually at the base. So we're getting the data, and the question is then what you do with that. Of course, we evaluate the groundwater levels for the groundwater flow pattern and also the change in groundwater levels. We look at the fluctuations in levels in leachate and try to tie it into whether the cap is performing or whatnot. And we're looking also at the leachate quality. We're looking at leachate impacts in groundwater and trends in it. And I'll talk to that in a bit about the various parameters that we were looking for. And we compare landfill gas readings to trigger levels for methane. We have a fairly extensive network of vapor monitoring wells, like I said, and also a lot of them towards the residential areas. And what we have with when we have the data, we look at whether those results are in line with previous post-closure information. So if there's any trends, if there's any alarming new findings, and we figure out whether the program is still effective. As Mandy said, those closed landfills are not going away. So you want to make sure that you monitor them effectively. You don't do too little, but you also don't do too much, because you may have to monitor those for like decades and decades. And if we see alarming things, we need to evaluate whether we need to take corrective actions. And then the source of all evil is essentially the leachate. The leachate is the liquid that is present in a landfill as part of the waste, and the composition depends on the age of the landfill and of course of the type of the waste. And the composition, if the leachate is mature, as they call it, it will also typically be methanogenic and highly saline. It will have lots of organic contaminants like hydrocarbons, solvents, metals, and it's basically a fairly ugly substance. So to verify whether the leachate is actually affecting the groundwater quality, you need to look at specific parameters. Parameters that are useful are mobile and persistent parameters like chloride, boron, and also indicators of anoxic conditions, like basically figuring out what is the redox status of the groundwater. And part of those parameters are part of the routine water chemistry, like nitrate and sulfate. Others are part of the metal analysis that we typically do, and that's dissolved manganese and dissolved iron, but also parameters like nutrients like ammonia, and organic indicators like dissolved organic carbon and volatile organic compounds. Parameters that are always analyzed also according to the standards of landfills in leachate are parameters that are what I call water treatment related, like chemical oxygen demand and biochemical oxygen demand, total Kjeldal nitrogen, and metals like and typically they look for total metals. And the reason that they do these parameters, that if you ship or you truck the leachate off to a treatment plant, they want to know how they have to adjust the treatment and whether some of the metals end up in the treatment sludge and whatnot. So, but for groundwater analysis, those parameters are not that useful. When you evaluate the data, and this is part of the whole holistic look at things, you need to of course look at generic guidelines like the Alberta Tier 1. But it's really for this site not that useful because the upgradient groundwater is already highly saline. In the Tier 1 guidelines, for instance, the domestic use aquifer pathway is typically excluded for total dissolved solids concentration of 5,000 milligrams per liter, which the upgradient groundwater is already higher than that. Nitrate concentration in the upgradient water are excessive. They're about 200 milligrams per liter or greater, and the guideline is 3 milligrams per liter. And we have lots of exceedances for metals, manganese, copper, selenium, uranium. So what you want to look at is parameters that are abundant in the leachate, which is the dissolved organic carbon, ammonia, and hopefully are mobile, like chloride and boron. You also need to understand which VOCs, volatile organic compounds, are present in all the landfills and why they are there. Chlorinated solvents were way more used in the 70s and 80s than they are used now, and every closed landfill you see those compounds. But what you need to identify is whether a compound like perchloroethylene, which is a dry cleaning liquid, actually migrates goes into the leachate and then in anaerobic conditions actually shows up in different transition products. And typically the one that it ends up is vinyl chloride, and vinyl chloride is persistent in outside the landfill and has a very stringent guideline because it's quite toxic. Another thing you want to consider is the redox conditions. Especially in leachate, you have such reduced conditions that, for instance, a parameter like sulfate, the leachate concentrations are typically very low, also variable, while in a lot of the background and down gradient wells, the sulfate concentrations are much higher. So sulfate is, due to the redox conditions, not a very useful parameter. So the status of our work so far is that to date we just don't have the feeling that the downgrading monitoring wells are significantly impacted by leachate. We do have chloride concentrations that are typically greater than Tier 1, and those concentrations are likely related to leachate. But other indicators like boron, like DOC and ammonia are actually variably and quite low. So the actual impacts are quite limited. Partially due to the intercepted trench, the passive venting trench for landfill gas, we don't have much of a methane gas migration issue. We only find one concentration typically that is outside the trench that is higher than the trigger value in the landfill standards for landfills, and that is an isolated location. The conceptual site model and the additional assessments that we've done recently have helped us manage the site as efficiently and effectively as possible. And the risk management plan has been largely implemented. And related to the leachate management, but currently the city is in the process of deciding what needs to be done. And one thing that of course is it would be lovely to pump more leachate out, but there's a couple of concerns with that. First of all, the cost and the treatability of that leachate, but also if you pump too aggressively on the leachate, you might actually see adverse effects to the landfill by slumping waste, by cracking of the cap, and you might even also see more ingress of surrounding groundwater into the waste. So these things need to be evaluated, and the leachate recovery trial that was started 2 years ago will probably be continued to assess that further. And then there's time for questions if needed. And this is the information. If you have any questions, you can ask. You can call Mandy or myself, and we'll be willing to talk to you anytime.
Okay, thank you, Mandy and Franz. Yeah, great presentation, really interesting material. It was, I found it really interesting to see such a level of detail focused on the challenges of Lethbridge. Any questions from the attendees here? I don't see anything yet coming up in the question box. Okay, yeah, there is a question here from Maria. What would be the next what would be the next step if, let's say, it happens that leachate is found in the groundwater?
Mandy, you want to talk to that?
Sure, I guess it would depend on which well it's in, and that's why we have our risk management plan. It does give us kind of an outline of what we would do next. So I haven't really given it too much thought because we haven't had to implement any sort of plan to move quickly. Franz, what would a typical response be?
Well, there is leachate will not, based on the setting of this site, will not just suddenly pop up until something dramatic happens. Like if for instance, we would see a breakout of on one of the side slopes of the landfill. We do have leachate components in the groundwater, including the boron that I mentioned at one location, and chloride. There is a considerable distance, though, from to the nearest receptor, which is a water well that I think, and many probably know that. Like I think it's not used for potable water, like which is close to the shooting range, a couple 100 meters to the west. There is also the Oldman River, which is a considerable distance. We recently drilled into the Saskatchewan gravels, which is the most permeous location, and we think we had chloride concentrations of less than 100 in those newest wells. So we think we have it reasonably under control. Actions that were taken a few years ago to improve the performance of the cap and to increase the drainage of basically the surface water management will probably have limited the chances that we'll suddenly see a breakthrough of leachate. The site is, of course, also already has been capped for more than 30 years. So we don't expect many changes, and in a way, this site is acting as a natural attenuation landfill, the way like in British Columbia, a lot of landfills are actually operated. And I would say that given the local geology, that this one actually behaves quite nicely as an attenuation landfill.
Okay, thanks for the good detailed response, Mandy and Franz. We have a question from Brittany. What are some of the corrective actions that may need to happen if issues appear with the old closed landfills?
Would those have been covered by what Franz had just kind of described, or are
Yeah, I guess partly, I think some of this, probably the similar investigation methods. Is there anything specific that you would do for these, for the historic ones?
I guess it would just depend. That's when you start treating it as a contaminated site and look at what type of chemicals you have in your groundwater. I'm assuming that it would be the groundwater that would detect it first. It would depend on what it is and what the problem is, because every landfill is so different. What your issue would be would determine how you would respond. I can't even think of any specific scenarios. Franz, can you think of anything?
Well, it really depends on the setting, right? Like a lot of the closed landfills, and we see that in a lot of cities, larger cities and even smaller communities. Sometimes the developments kind of encroach onto that land because the landfills were often like just at the outskirts of the town, and then the town grows, and then suddenly they're in the town. But then it really depends on what kind of waste. Like the older landfills often would burn their waste, and then we've seen that a few times in closed landfills, that all you find is just burnt residuals, glass and yeah, charred material, which doesn't really create much methane gas because it doesn't ferment anymore. But if there then is no one nearby and you don't have gas and the groundwater is properly contained, then over time a lot of these contaminants attenuate. But you need to be careful. Like we have various closed sites with where the chlorinated solvents are persistent and moving to potential receptors, whether it's like creeks or stagnant water bodies or water wells. So every site has its own pros and cons, and as we said, a holistic view, like looking at the site overall, like gases, materials, chemicals of concern, would basically give you the approach for a site.
Okay, thanks. Brittany, hopefully that answered your question. If you wanted something more specific, fire another question in there and we can see what they have. We have a question here from Robert Harriet. Although wetlands can attract birds, which may not be welcome, have you considered using engineered wetlands to treat leachate?
Well, I would say for this site that leachate treatment in a natural setting is just not an option, specifically because of the fairly excessive and actually uniquely high chloride concentrations. Leachate treatment is difficult, and I think that you need to be very careful in that you don't accumulate impacts, like for instance, like metals into a natural setting. So most of the leachate, as far as I know, will be treated in municipal water treatment plants, on site in treatment units, or deep well disposed.
Okay, thanks, Franz. Any other questions? Not hearing any other questions or seeing anything. Good participation though. Thanks for those questions, and thanks for the great answers, Mandy and Franz. Thanks also to Trevor for your presentation as well. I'll turn it back over to Joe.
Thank you, Tyler, for moderating that session, and thanks for the last two presenters for wrapping up our first day of virtual EnviroTech. I personally think it went pretty well, all things considered, our first try at it. We started off the day with some regulatory updates, then moved into some GHG and climate change matters, and then we looked at water, and we closed off with landfills. And tomorrow we have a look at some technology presentations, a little bit of everything, some soils, some remediation, salt, and then we'll close with a hot topic of emerging contaminants. Once again, thank you to all of our sponsors, North Shore, Diamond sponsor, and then all of the companies that were on board for the original in-person version of EnviroTech that has stayed on for us this year. We really appreciate it. And thank you to our speakers, and thank you to everyone who registered and are continuing to register. We really appreciate the support. It means a lot, and your industry association really appreciates it. It helps us. So thank you. We'll see you tomorrow morning. Have a great night and get outside and enjoy the sunshine. Thank you and take care.